Hi everyone, welcome to goclasses. In this lecture, we will continue our discussion of GATE and TIFR PYQs, previous year questions. Based on these topics, vertex cover matching independent set and clique in graph theory. So this is GATE and TIFR PYQs part 3. The previous two parts you can find in this playlist. On YouTube, you can search Discrete Mathematics Go classes, and this playlist will be there. Discrete Mathematics GATE PYQs Compact Course Practice Questions and Revision playlist. So in this playlist you can find the previous GATE and TIFR PYQs part, basically part 1, part 2. Okay, so let's continue our discussion. Let's solve GATE and TIFR questions PYQs on the topic matching. What is a matching? In a graph, in an undirected graph, matching is basically set of edges which are pairwise non-adjacent. So in the GATE and TIFR, there are many questions based on matching. Let me tell you, all the questions based on matching, they are basically asking to count number of matchings, or to count number of perfect matchings, to count number of maximal matchings, to count number of maximum matchings, and also relationship between matching and vertex cover. So these type of questions have been asked in GATE PYQs and also TIFR PYQs. You can see this is TIFR 2022 question. They are asking number of maximal matchings in this path graph on 6 vertices. This is TIFR 2022 question, and this is based on relationship between matching and vertex cover. So you can see there are questions based on relationship between matching and vertex cover, and there are questions based on counting the number of matchings, counting the number of maximal matchings, perfect matchings, and so on. Okay, so this TIFR 2022 question, which is asking you to find, which is asking you to count number of maximal matchings in this path graph on 6 vertices, this we have already done in the previous lecture. Okay, in the previous part, this we have already done. The link you can find in the description, also in the pinned comment, you can check it out, or you can search Discrete Mathematics Go classes on YouTube, and in this playlist you can find the part 2, part 1. Also in the previous part, this TIFR 2022 question we have also solved. Okay, so this question based on relationship between matching and vertex cover, this also we have done in the part 2. Now these are GATE PYQs based on counting number of perfect matchings, counting number of matchings. These we will solve in this lecture. Okay, you can see this is GATE 2003 question. It is asking you to count number of perfect matchings in a complete graph on 6 vertices, and this is GATE 2026 question. So this is latest question. This is asking you to count number of matchings in a path graph on 8 vertices. So these two questions we are going to solve in this session. Okay, remember I told you in the previous lecture that in any graph, to count the number of matchings, to count the number of perfect matchings, to count the number of vertex covers, to count the number of independent sets, to count the number of maximal matchings, to count the number of maximal, or I can say maximum independent sets, so to count the number of cliques, edge covers, you just think recursively. Very simple. In any graph, if they ask you to find the number of matchings or independent sets or vertex cover or edge cover or cliques, then always think recursively, means count recursively. Already in the previous part, we have done multiple questions where we were thinking recursively and we were finding the number of independent sets, the number of matchings. Okay, so some questions we have done in the previous lecture, in the previous part, part 2, and some questions we will do in this part. Okay, so by the end of this lecture, by the end of this part, I can say you will become expert in thinking recursively to count number of matchings, independent sets, vertex cover, cliques, edge covers. Okay, let's all get 2026 question, latest question. G is undirected graph which is a path on 8 vertices. So basically this G, this is a path graph on 8 vertices. This is basically P8. The question is asking the number of matchings in G. How many matchings are there? Remember, the question is not asking for maximal matchings. In the previous part, in the part 2, we have already solved a question where there was a path graph given and they were asking you to find number of maximal matchings in path graph. That question we have already solved in the part 2. In this question, in this gate 2026 question, they are asking number of matchings. Okay, so this is a note. In any graph, to count number of matchings or to count number of maximal matchings or to count number of perfect matchings, always think recursively, means you count recursively. Same goes for counting number of independent sets. And if you want to count number of vertex covers or number of cliques in a graph, how many cliques are there, how many vertex covers are there, then think of relationship between independent set, vertex cover and clique. We have already seen in our previous lectures where we were discussing the concepts that what is the relationship between independent set, vertex cover and clique. Okay, so if the question asks you to count number of vertex covers or to count number of cliques in a graph, then think about the relationship between independent set, vertex cover and clique. Don't worry, by the end of this lecture it will become clear what I want to say. Okay, I will discuss how to count number of vertex covers, how to count number of cliques at the end of this lecture. Okay, so let's see. In this gate question, we need to find number of matchings in path graph on 8 vertices. Let me tell you, we will think recursively. We will find for Pn, not for P8. The question is asking for P8, but we will find for Pn, means if you have path graph on n vertices, then how many matchings are there? Remember, we will think recursively and we will find the general formula and then we can easily find the answer for P8. But if you solve this question manually for P8, if you apply the brute force or if you solve it manually, then it will take a lot of time. It will consume a lot of time because there are 8 vertices. We have path graph on 8 vertices and it is asking number of matchings. So the brute force method, the manual method will consume a lot of time. Here you must apply the recursive thinking. Okay, so that we will see now. So we will see these two questions. You can see these are general questions. How many matchings are there in a path graph on 8 n vertices? So the number of matchings in Pn, and also how many maximal matchings are there in Pn, path graph on n vertices. For to answer both these questions, we will think recursively. Okay, and you will see the difference when we think recursively. To find number of matchings, to find number of maximal matchings in Pn, path graph on n vertices, you will see the difference. When we find number of matchings, then we will think about matching only. And when we find number of maximal matchings, then we will think about maximal matching. Okay, you will see the difference. We will answer this question also, this question also. Actually, this second question we have already answered in the previous part, in the part 2. You can find the link in the pinned comment in the description. This actually we have already done in the previous part, but here again I will solve it quickly. I will solve it. The reason is I want to show you the difference between matching and maximal matching, means how to count, how to think recursively to count number of matchings and how to think recursively to count number of maximal matchings. I want to show you the difference between these two. That is the reason this question also we will solve, this question also we will solve. Okay, so let's start. First, let's find the number of matchings in a path graph on n vertices. Here, a path graph on n vertices is given to you, Pn. So it is basically path graph on n vertices, vertex 1, vertex 2, 3, 4, and so on n. So this is a path graph on n vertices. We need to find number of matchings in this Pn path graph on n vertices. So let's assume that Sn, this is the number of matchings. I am assuming that Sn is the number of matchings in Pn. Pn is the path graph on n vertices, and Sn, this is the number of matchings in Pn. So you can easily find S1, S2 manually. Yes or no? Base cases you can easily find. So let me write the base cases. The base cases will be when you have path graph on one vertex, when you have path graph on two vertices. Okay, so tell me what will be S1? S1 means the number of matchings in path graph on one vertex, what will be the number of matchings? Here there is no edge in this path graph on one vertex. There is only one vertex, there is no edge. And what is a matching? Matching is set of edges which are pairwise non-adjacent. So this is pairwise non-adjacent edges. Non-adjacent edges. In this path graph on one vertex, how many matchings I can create? Only one matching I can create, that will be empty set, because remember there is no edge in this path graph on one vertex, and matching means set of edges which are pairwise non-adjacent. So one matching I can create, that will be empty set. This empty set, this is a matching. Yes, this is a matching. This is a matching. Okay, you can see this empty set. This does not have anything, but the point is there is no violation of matching. Matching is a set of edges which are pairwise non-adjacent. Here you can see this is a set of edges. Of course, there is no edge in it, but the point is this is a set. This empty set is a matching. So in this path graph on one vertex, there is one matching. So S1 will be 1. What about S2? The number of matchings in path graph on two vertices. Here I can create total 2 matchings I can create. You can see I can take this as, so that will be a matching. I can take this as 1, 2. Or if I don't take any as, then this empty set will be a matching. So these are the 2 matchings I can create in this P2. Very simple. What about P3? What about P3? 1, 2, 3. This is the path graph on 3 vertices. How many matchings can you create here? S3 means the number of matchings in P3. So you can see if you don't take any edge, then that will be a matching. If you don't take any edge. So let me write it here. You can see one matching is empty set. Next, if you take this edge or if you take this edge, so basically we will have 2 more matchings. Yes or no? You can see 2 more matchings we will have. Either I can take this as 1, 2, or I can take this as 1, 2, 3. Okay, that's it. I cannot create any other matching because matching is set of edges which are pairwise adjacent. Okay, so this matching, this is basically set of edges. Okay, so these are the base cases. We have found S1, S2, S3. These are the base cases. What is Sn? This is the number of matchings in Pn, and these are the base cases. Now let's find what is Sn. Can we think recursively for Sn? Can we count recursively this Sn? Okay, so let's see. Let me write just quickly what is this Sn. This is number of matchings. This is number of matchings in Pn. Okay, so let's see what this Sn will be. Just focus on this age. Focus on this age. Okay, let's focus here. Matching means set of edges which are pairwise non-adjacent. So just focus on this age 1, 2. In a matching, either we will take it or we will not take it. Only 2 possibilities are there. Correct? So I can say that number of matchings which contain 1, 2 plus number of matchings which do not contain 1, 2. Only these 2 possibilities are there. Means this age 1, 2 is in matching. Okay, is in matching. Either this possibility is there that I take this age 1, 2 in the matching, or this age 1, 2 is not in the matching. This age 1, 2 is not in matching. Only these 2 possibilities are there. Either this will happen or this will happen. Very simple. So how many matchings are there which contain age 1, 2? Let's find that. If I take this age 1, 2 in the matching, I have already taken this age 1, 2 in the matching, then tell me how many matchings I can create which contain age 1, 2. If you have already taken 1, 2 in the matching, then definitely this age 2, 3 you cannot take. Correct? And we are creating matching, not necessarily maximal matching. Our target is to create matching. Our target is not to create maximal matching or perfect matching like that. Okay, so how many matchings are there which contain the age 1 2? If I take this 1 2 as in the matching, then 2 3 as I cannot take in the matching. Now in this remaining graph I can create a matching. Yes or no? In this remaining graph I can create matching. In this remaining graph I can create any matching I can create. Okay, so very simple point. Remember, how many matchings are there which contain the age 1 2? So that will be same as how many matchings are there in this graph, in this remaining graph. What is this remaining graph? This is a graph, path graph on n minus 2 vertices, so this is p n minus 2. And how many matchings are there in this p n minus 2? That will be s n minus 2. What is Sn? This is the number of matchings in Pn. So what will be number of matchings in Pn minus 2? That will be Sn minus 2. Very simple. I hope you understood. Remember, how many matchings are there in this path graph on n vertices? That is Sn. Now, in any matching, either this age 1 2 will be there or it will not be there. So only two cases are possible. First, let's find how many matchings are there which contain this age 1 2. Already this age 1 2 is there in this matching, so 2 3 age I cannot take. Now in the remaining graph I can create any matching I can create. How many matchings I can create in this remaining graph? That is Sn minus 2. So number of matchings that contain 1 2, that is same as Sn minus 2. Means how many matchings you can create in this remaining graph, that will be the number of matchings containing this age 1 2. Very simple. I hope you understood. Now what about this? We have already found this Sn minus 2. Now let's focus on this. Means when this age 1 2 is not in the matching, how many matchings are there which do not contain this age 1 2? So this age 1 2 is not there in our matching. Now is it necessary that this 2 3 age we need to take in the matching? Tell me. Very simple question I am asking. If this age 1 2 is not there in the matching, is it necessary that this age 2 3 I must take in the matching? No, it is not necessary, because we are not finding maximal matching. We are just finding matching. Okay, yes or no? So it's not necessary that this 2 3 I must take or this 3 4 I must take like that. Yes or no? So how many matchings I can create which do not contain this age 1 2? So very simple. In this remaining graph I will create matching. Yes or no? In this remaining graph I will create matching. Create matching, find matching. Create matching here. What is this remaining graph? This is path graph on n minus 1 vertices. How many matchings are there in this path graph on n minus 1 vertices? That is Sn minus 1. That's it. I hope you understood. Is this clear to everyone? So remember, in this path graph on n vertices, how many matchings I can create which do not contain the age 1 2? If you do not take this age 1 2, then in this remaining graph you can create a matching. So how many matchings you can create in this remaining graph? That will be Sn minus 1, because this remaining graph, this is Pn minus 1. Number of matchings in Pn minus 1, that is Sn minus 1. That's it. Very easy. Tell me, this recurrence relation will work for how many vertices? Means the number of vertices, what it must be? Means this n, this should be what? Tell me. So you can see this n value, this must be the number of vertices, or I can say this n value, this must be greater than equal to 3, because if you take 3 as 3 is equal to s1 plus s2, we have already found manually what is s1, what is s2, correct? But remember, this recurrence relation will not work when you put n equal to 2. If you put n equal to 2, then we will get s0 plus s1, but we don't have s0, because remember, there is no path graph on 0 vertices. In every graph at least one vertex should be there. So very simple point, that this recurrence relation will work when you have n greater than equal to 3. I hope you understood. So finally I can say that number of matchings in path graph on n vertices, that will be s sn is equal to Sn minus 1 plus Sn minus 2, where n is greater than equal to 3. Okay. And what are the base cases? Base conditions we have already found. Base cases are, what was S1? That was 1. And what was S2? That was 2. Correct? So these are the base cases. Now you can easily find what will be S3, S4, and so on. But this is basically our general formula. This is our general formula for the gate 2026 question. Okay, is this clear? The gate 2026 question was asking number of matchings in P8, and we have found number of matchings in Pn. Now you can just put n equal to 8 and you will get your answer for gate 2026 question. Correct? So let's find what will be P8. Here you can easily see what will be S3. S3 will be S1 plus S2. So that will be, I can say S1 plus S2. That will be 3. What will be S4? S4 will be S3 plus S2. S3 plus S2, that will be 5. So like that, you can get what will be S5. Actually, if you notice this recurrence relation, this is a Fibonacci series, right? Okay, this recurrence relation, if you see, this is basically your Fibonacci series. This is basically your Fibonacci recurrence relation. Okay, so means every value is summation of previous two values, right? So for example, S5 will be the summation of previous two values 8. For example, S6 will be summation of previous two values, that is 13. S7 will be summation of previous two values, that is 21. And S8 will be summation of previous two values, that will be 34. This is our gate 2026 question. This is the gate 2026 question. So the answer will be 34. I hope you understood. Is this clear to everyone? So you can see this was our gate 2026 question. It was asking the number of matchings in path graph on 8 vertices. So this was basically path graph on 8 vertices. The number of matchings in P8, that will be 34. I hope you understood. Is this clear? Let me know. This recursive thinking, did you understand? Now, let's find the number of maximal matchings. And I will show you the difference between thinking recursively for matching, thinking recursively for maximal matching. There is a difference. Okay, so let's focus on this difference, or let's find the number of maximal matchings. So for a moment, let me assume that yn, this is number of maximal matchings in Pn. So what is yn? Number of maximal matchings in Pn. Now let's see how to think recursively for maximal matchings. First of all, let's find the base cases and then we will think recursively. So let's find the base cases. Base cases means if you have path graph on one vertex, path graph on two vertices, path graph on three vertices, then what will be yn? Means what will be number of maximal matchings in these graphs. So you can see P1, P2, path graph on two vertices, P3, path graph on three vertices. So what will be the number of maximal matchings in P1? Means what will be y1? Tell me, what will be y1? Y1 will be 1 because in this graph, there is no edge. There is only one vertex, path graph on one vertex. So How many maximal matchings I can create? This empty set will be a maximal matching. Yes or no? This is a maximal matching. This is a maximal matching in P1. Okay, this empty set. Because what is matching? Remember, matching is set of edges which are pairwise non-adjacent. And what is maximal matching? Maximal matching is a matching which cannot be extended further. Okay, or I can say that maximal matching is a matching which is not subset of another matching, which is not proper subset of another matching. So this is the definition of maximal matching, that maximal matching is a matching which is not proper subset of another matching. Very simple. Okay, or I can say that maximal matching is a matching that we cannot make it bigger by adding something to it. Okay, so you can see in this path graph on one vertex there is only one maximal matching, that is empty set. What about this path graph on two vertices? What will be y2? Y2 means number of maximal matchings in P2. So here empty set will not be a maximal matching, because I can add this age and I can get a bigger matching. Yes or no? So I can say that there is only one maximal matching here. Okay, in this P2 there is only one maximal matching, and that will be this age 1 2 I have to take. Remember, empty set I cannot create now. If you create empty set, then that will be a matching, that is fine, but that will not be maximal matching because I can add this age and I can make it bigger. So in this path graph on two vertices, the number of maximal matchings will be 1. What about this path graph on three vertices? What will be the number of maximal matchings? To create maximal matching, either I can take this age or I can take this age. That's it. So the number of maximal matchings will be 2. Either I can take this age 1 2 or I can take this age 2 3. Okay, so these are the base cases. Now let's see how to think recursively to find the number of maximal matchings in path graph on n vertices. Let's think recursively. Let's write this yn in terms of smaller, I can say smaller path graphs. Okay, or I can say let's write this yn in terms of yn minus 1, yn minus 2, yn minus 3, and so on. Okay, so let's find the recurrence relation for yn. What yn will be? Again, you just focus on this age. Just focus here. We are finding the number of maximal matchings in this path graph on n vertices. So just think about maximal matching. Don't only think about matching, think about maximal matching. We need to find matching which is as big as possible, means we cannot make it bigger by adding something to it. Okay, that is the definition of maximal matching. Maximal matching is a matching which is as big as possible, but we cannot make it bigger by adding something to it. Okay, remember, maximal may not be the largest. Maximal simply means that it is a matching to which we cannot add something new and make a bigger matching. This is the idea. Okay, so let's see what will be yn. You can see either this age I will take in the maximal matching or I will not take. So just focus on this age. I can say that only two possibilities are there. In the maximal matching, this age will belong or this age will not belong. Okay, so I can find the number of maximal matchings which contain this age plus number of maximal matchings which do not contain this age, and then I can add them. Okay, yes or no? So there are only two possibilities, that this age 1 2, this age 1 2 is in maximal matching, or this age 1 2 is not in maximal matching. Only these two cases are possible. Either it will happen or it will happen. Okay, so because of or we are adding them. Okay, so how many maximal matchings are there which contain this age 1 2? So just focus on this. Means let's assume that this age 1 2 I have taken in the maximal matching. Now, how many maximal matchings we have containing this age 1 2? If you have taken this age 1 2, then definitely this 2 3 age we cannot take in the maximal matching. Now remember, in this remaining graph, In this remaining graph, you can find maximal matching. Yes or no? In this remaining graph, you can find maximal matching. Here you can find maximal matching. You can create maximal matching. Okay. What is this remaining graph? This remaining graph actually that is Pn minus 2. Yes or no? This is a path graph on n minus 2 vertices. So this remaining graph, this is basically Pn minus 2. And what is the number of maximal matchings in Pn minus 2? That will be Yn minus 2. Because what is Yn? That is number of maximal matchings in Pn. So number of maximal matchings in Pn minus 2, that will be Yn minus 2. Very simple. Did you understand this? Actually, this we have already seen in the part 2 also, in the previous part. So here you can see the number of maximal matchings that contain this age 1, 2. Already this age 1, 2 we have taken in the maximal matching. So definitely this age 2, 3 we cannot take. Now in this remaining graph, you can create a maximal matching. Very simple. Okay. Now what about this? Means what is the number of maximal matchings that do not contain this age 1, 2? Already this we found Yn minus 2. Now let's see this one. Means this age 1, 2 we have not taken in the maximal matching. Just tell me a simple question. If I do not take this age 1, 2 in the maximal matching, is it necessary that this age 2, 3 I must take in the maximal matching? Is it necessary? Yes, that is necessary. Because let's assume you don't take it. Let's assume you don't take it. And here if you create a matching, then that will not be maximal. Because in that matching, you can add this age 1, 2. You can see here, look at all the edges. They are non-adjacent to this age 1, 2. This age 1, 2 is non-adjacent to these remaining edges. So in this remaining graph, if you create a matching, that will not be maximal, because you can add this age 1, 2 to that matching and you can make it bigger. So what I am saying that if you don't take this age 1, 2 in the maximal matching, then it is necessary that you must take this age 2, 3 in the maximal matching. Because if you don't take it, and then if you create the matching in the remaining graph, then that will not be maximal. Okay. So to find maximal matching, remember, if you don't take this age 1, 2, then definitely this 2, 3 age you must take. So you can see here, this implies this. I hope you understood this point. Okay, and I hope you also understood the difference between thinking recursively for maximal matching and thinking recursively for matching. Did you notice? When we were thinking recursively only for matching, then in this remaining graph we can create any matching. But here you can see, when you are thinking for maximal matching, then in this remaining graph you can see this age 2, 3 you must take. Because if you don't take this age 2, 3, then whatever matching you will create here, that will not be maximal, and we want maximal matching. I hope you understood the difference. I just want to show you the difference between thinking recursively for matching and thinking recursively for maximal matching. Did you understand this difference? Let me know. So you can see how many maximal matchings are there which do not contain this age 1, 2. Then definitely this age 2, 3 you must take. If you take this age 2, 3, then definitely this age 3, 4 you cannot take. Now in this remaining graph you can create any maximal matching. Okay, in this remaining graph, this is path graph on n minus 3 vertices. In this remaining graph you can create any matching, any maximal matching you can create. Any maximal matching you can create here. What is the number of maximal matchings in Pn minus 3? That will be Yn minus 3. Okay, that's it. So finally I can say that Yn, this will be equal to Yn minus 2 plus Yn minus 3. Okay, and this recurrence relation will work when n is greater than equal to 4. Because if you put n equal to 3 here, then we will get y3 equal to y0 plus y1. But we don't have y0 because there is no path graph on 0 vertices. Every graph must have at least one vertex. So you can see that you can start with y4. That will be y2 plus y1. y2, y1 we have already found manually. These were the base cases. So very simple. This is the recurrence relation for number of maximal matchings in path graph on n vertices. Okay, is this clear? And what are the base cases? Let me quickly write here. What were the base cases? What was y1? What was y2? What was y3? y1 was 1, y2 was also 1, and y3 was 2. Correct? Okay, these were the base cases. One more thing you can see. We have also found what was Sn. Sn was number of matchings. Sn was number of matchings in Pn. Okay. In the same graph, in the path graph on n vertices, yn means number of maximal matchings, Sn means number of matchings. Okay. Here you can see. So, what was the recurrence relation for Sn? We have already seen. Sn that was equal to Sn minus 1 plus Sn minus 2. So, there is a difference here. You can see. In the recurrence relation for number of maximal matchings in Pn, we have yn equal to yn minus 2 plus yn minus 3. And you can see in this recurrence relation for number of matchings in Pn, we have Sn equal to Sn minus 1 plus Sn minus 2. Okay. And here n greater than equal to 3. And what were the base cases that you already know? Base cases were, let me write it here. Base cases were S1 was 1 and S2 that was 2. Okay, that's it. So this is the complete analysis. I hope you understood. For a path graph on n vertices, what is the number of maximal matchings? What is the number of matchings? So we have done the complete analysis, and I hope you understood the difference between thinking recursively for maximal matching, thinking recursively for matching. Okay, so we have done the complete analysis of this gate PYQ, this gate 2026 question. The complete analysis we have done. I hope you understood. Let's solve gate 2003 question. How many perfect matchings are there in a complete graph of 6 vertices? So a complete graph of 6 vertices. Remember, complete graph means every 2 vertices are adjacent. Between every pair of vertices, there is an edge. Okay, that is your complete graph. So in a complete graph of 6 vertices, how many perfect matchings are there? What is a perfect matching? It is a matching that covers all the vertices. Okay, a matching covering all the vertices, that is called perfect matching. So let's solve this question. Let me tell you, there are 2 methods to solve this question. We will see both the methods. Then we will see the general solution for K2n. Here you have 6 vertices. Basically, if you have complete graph on even number of vertices, then what will be the general solution? For example, complete graph on 8 vertices, 10 vertices, 12 vertices, then what will be the general solution? Remember, if you have graph on odd number of vertices, then how many perfect matchings will be there? If they give you graph on odd number of vertices, the number of vertices is odd, then how many perfect matchings will be there? Answer is 0. Because if your graph contains odd number of vertices, then there is no matching which is perfect. Means there is no perfect matching. So the number of perfect matching will be 0. Okay. And remember, if your graph has even number of vertices, then perfect matching may or may not exist. This we have already seen in our lectures. I told you that if your graph has odd number of vertices, then perfect matching does not exist. So number of perfect matching 0. And if your graph has even number of vertices, then perfect matching may exist or may not exist. Actually, for a complete graph on 6 vertices, perfect matching exists. Okay, we will see what is the number of perfect matchings in this K6. But we will also see the general solution for a complete graph on even number of vertices using 2 methods. And some variations also we will solve for this gate 2003 question. So let's solve it. Let's see the 2 methods to solve this question for K6. First, let's do quick revision of some concepts that are very useful. What is adjacent edges? What is non-adjacent edges? Because remember, what is a matching? Matching is basically set of edges which are pairwise non-adjacent. Matching is pairwise non-adjacent edges. Okay, so we must know what are non-adjacent edges, what are adjacent edges. This is just a recap in our concepts. In our lectures, we have already seen all these concepts. So let's see what is adjacent edges and non-adjacent edges. So two edges in a graph are called adjacent if they have a common vertex, or I can say if they have a common endpoint. And what are non-adjacent edges? If they do not share any common vertex, if they do not have any common endpoint. So let me show you how the adjacent edges look like. Adjacent edges, how they look like, and non-adjacent edges, how they look like. See, adjacent edges have a common vertex, or I can say a common endpoint, right? So they will look something like this. For example, AB, AC. You can see they have a common vertex. Okay, these two edges. For example, they will look like this: BC, AC. You can see they have a common vertex. So very simple. This is how adjacent edges will look like. Is this clear? Very simple. And what about non-adjacent edges? How they look like? Non-adjacent edges, they do not share any common vertex. They do not have any common endpoint. So they will look something like this, that AB, CD. Very simple. Okay, they will look something like A1, A2, A3, A4. And adjacent edges, how they will look like? They will look like A1, A2, A1, A3. Okay, I hope you understood. Very simple. So when you have non-adjacent edges, then all these vertices which they are covering, these vertices will be different vertices. Okay, because non-adjacent edges do not share any common vertex, any common endpoint. Correct? So I hope you understood how non-adjacent edges look like and how adjacent edges look like. Now, we have already seen in our lectures, but let's do the recap. In any graph, how a matching looks like. Remember, matching is set of edges which are pairwise non-adjacent. Means every two edges have disjoint vertices. Okay, whatever two edges you take, they have disjoint vertices. Because non-adjacent edges means they do not share any common endpoint. So non-adjacent edges have disjoint vertices. Very simple. So how a matching looks like? If M is a matching, any graph you take, if M is a matching, matching means set of edges which are pairwise non-adjacent. So set of edges. So for example, if a edge is A1, B1, then this edge cannot have vertex A1. Also, this cannot have vertex B1, right? So it will be having A2, B2. Okay. Then A3, B3. I hope you understood. And then so on. You can see AK, BK. Okay, is this clear? Very simple. And remember, all these vertices, they will be disjoint, or I can say they will be different, distinct. Correct? You can see, because these are edges. Total, how many edges are there? There are total K edges. Okay. And remember, all these vertices, A1, A2, A3, and so on, B1, B2, B3, and so on, all these 2K vertices, they will be distinct. Okay, you can see here, this M, this matching M, this covers total 2K vertices. 2K vertices. Okay, and remember, all these vertices, these are distinct. Okay, here I can say that all these vertices, like this vertex, this vertex, this vertex, this vertex, all these vertices, all these vertices, these are distinct vertices, different, or I can say distinct. Okay, I hope you understood. So remember, matching is set of pairwise non-adjacent edges. Non-adjacent edges have disjoint vertices. They cover disjoint vertices, or I can say distinct vertices. Here you can see, if you have this matching with K edges, every edge will cover two vertices. But you can see these are non-adjacent edges, so they will cover distinct, or I can say different or disjoint vertices. So you can see all these vertices, these are distinct vertices. So I can say this matching covers total 2k vertices, 2k unique vertices, I can say 2k different vertices. So this matching covers 2k different vertices. Very simple. Now, how a perfect matching looks like? Perfect matching is a matching which covers all the vertices. So if you have a perfect matching, let's call it PM. Of course, it is a matching, so it will be set of edges which are pairwise, non-adjacent. So it will be having edges like A1 B1, A2 B2, A3 B3, and so on, AK BK. Okay. The point is this perfect matching will cover all the vertices. So if you see the number of vertices in the graph, that actually will be 2k. Okay, all the vertices of the graph are actually covered by this perfect matching. So remember, this perfect matching, this is also a matching. Here you can see there are total k edges here. Okay, the point is that these are 2k different vertices. Okay, this perfect matching, this covers 2k different vertices, and all the vertices of the graph are covered here. Okay, yes or no? So I can say that number of vertices in the graph, the size of VG, okay, number of vertices in the graph, that also will be 2k. Okay, means all the vertices are covered by this perfect matching. All vertices of G are covered by perfect matching. Okay, that's it. I hope you understood. So remember, all these vertices A1 B1 A2 B2 A3 B3 and so on AK BK, all these vertices will be different vertices. So this perfect matching covers 2k different vertices, and because it is a perfect matching, so it is covering all the vertices, means only these are the vertices of the graph, means all the vertices of the graph are covered. So the number of vertices in the graph, that will be 2k. Okay, that's it. So this is how a perfect matching looks like, and this is how a matching looks like. The difference is only a small difference, that in a perfect matching all the vertices of the graph must be covered. Okay, very simple. Now in this gate 2003 question, they are asking how many perfect matchings are there in K6 in complete graph on 6 vertices. So let me tell you, there are two methods. Let's see the method number 1. Method number 1. You can decide which method is better, but let's see the method number 1. Remember, what is our question? Our question is, we have K6. Okay, K6, and we need to find number of perfect matchings. This is what we need to find, number of perfect matchings. Now for a moment, let's assume that in this K6, let's assume that vertices are 1 2 3 and so on 6. Okay, or 1 2 3 4 5 6. These are the vertices. Okay, so because this is a complete graph on 6 vertices, it means every two vertices are adjacent. Agree? Yes or no? Every two vertices adjacent. Whatever two vertices you will take, they have edge between them. Every two vertices adjacent. Correct? Okay, so now let's see the method number 1 to find the number of perfect matchings. You can see, if you are creating a perfect matching, then it is necessary that this perfect matching will be having 3 edges. Do you agree with me? In this K6, how a perfect matching will look like? Just tell me that point. See how a perfect matching will look like in this K6. How a perfect matching looks like in K6. Can anyone tell me? Perfect matching will cover all the vertices, and perfect matching, remember, this is a matching, means this is set of edges. So how many edges will be there? There will be exactly 3 edges. Yes or no? Which are pairwise non-adjacent. So you can see There will be exactly 3 edges. For example, you can have 1 2 3 4 5 6. Okay, yes, this is a perfect matching. It is covering all the vertices. You can see every two edges, they are non-adjacent. They are not having any common endpoint. You can see all the 6 vertices are covered. So this is a perfect matching. I hope you understood. So how a perfect matching looks like? For example, I can take 1 3, I can take 2 6, I can take 4 5. This is also fine. For example, with 1, if you take, let's assume 4, with 1 you are taking 4, with 2 you can take 6, with 3 you will have to take 5. Okay, yes or no? This is how perfect matchings will look like. The point is, there will be 3 edges. Exactly 3 edges will be there. There will be a partner of 1. Then we will find partner of the remaining vertices also. Yes or no? Like that. I hope you understood. Okay. So now let's see how many matchings, how many perfect matchings will be there here. So perfect matching. If I'm creating a perfect matching, just tell me a simple point I'm asking. It is guaranteed that I must cover the vertex 1 because perfect matching will cover all the vertices. So I must cover 1. So I must take a edge which is incident on 1. Okay, yes or no? Matching is set of edges. Matching is set of edges. So I must take a edge which covers 1. This is guaranteed. Whatever perfect matching I create, I must take a edge which is incident on 1. Now tell me, for this edge, how many choices I have? Or I can say, for this partner, how many choices I have? This partner of 1, how many choices I have? I have 5 choices. I can take any of them. Okay, yes or no? Because this is complete graph. So between every two vertices, there is edge. Every two vertices are adjacent. So I can say that with 1, I am finding a partner. So tell me how many choices I have? How many choices? There are total 5 choices. Okay, for partner of 1, there are 5 choices. Very simple. Now, once you have fixed a choice, once you have done this work, remember we need to do this work also, this edge also, and this edge also, and this edge also, because perfect matching will have exactly 3 edges. So remember, here this work also we need to do, this work also we need to do, this work and this work and this work. There is and here. Now focus on this work. I am finding the partner of 1. For partner of 1, there are 5 choices. What are the 5 choices? Either I can take 2, or I can take 3, or I can take 4, or I can take 5, or I can take 6. These are the 5 choices. Now, once I complete this work, let's assume that I have taken 3. For a moment, assume that I have taken 5. Okay, just for a moment, assume this 5 I have taken. So it means that I have taken this 1 5. Okay, like that. I hope you understood. The point is, for this partner of 1, there are 5 choices. Now, once this task is over, to complete this task, one of them I have to choose. Let's assume I have chosen 5. Now this task is over. Now I need to complete the remaining 2 tasks also. You can see, after finding the partner of 1, now what are the vertices that are remaining? Just tell me this point. With 1 I have found the partner 5. How many vertices are remaining? These 4 vertices are remaining. So I need to cover them also. Perfect matching will cover all the vertices. I need to cover these remaining vertices also. So let's take the minimum numbered vertex, means let's find the partner of 2. In these remaining vertices, who is the minimum numbered vertex? That is 2. So let's find the partner of 2. Okay, let's find the partner of 2. For this 2, I need to find a partner. How many choices I have? Tell me how many choices I have for this partner of 2. How many choices I have? You can see, I cannot take 1 comma 5. For this 2 as a partner, there are 3 choices. Yes or no? There are 3 choices. What are the 3 choices? The 3 choices are either 3 or 4 or 6. Correct? Okay, let's assume that I have taken this 4. Means as a partner for 2, I have taken this 4. So now this task is also over. Okay, Yes or no? With this 2, I have found the partner, that is 4. This partner I have found. Very simple. Now, how many vertices are remaining? 2 vertices are remaining. Okay. So, what is the minimum numbered vertex? That is 3. Now, let's take this 3. How many choices are there for partner of 3? Only one choice. I have to take this 6. Yes or no? So, here there is only one choice. Okay, I have to take this as 6. I can say this 3, 6. Okay, correct? With this 3, I have to take this 6. So, finally, what will be the number of perfect matchings? How many perfect matchings I can create? That will be 5 into 3 into 1. 5 into 3 into 1. That will be 15. Okay, is this clear? Total 15 perfect matchings I can create. Did you understand this? Very easy method, remember. Few things you have to understand, that the given graph is complete graph. So between every two vertices, there is edge. Or I can say every two vertices are adjacent. We need to find perfect matching. Matching is set of edges. Perfect matching will cover all the vertices. All the vertices must be covered, and because you have K6, so in the perfect matching, there will be exactly 3 edges, because matching means set of pairwise non-adjacent edges. So any two edges must not have any common vertex. Yes or no? Or I can say every two edges must be covering different or disjoint vertices. Yes or no? So you can see that to cover all the vertices, I must cover the vertex 1 also. So I will find the partner of 1. There are 5 choices. Now, once I have found a partner of 1, then I will see what are the remaining vertices. In the remaining vertices, who is the minimum numbered vertex? That is 2. So for this 2, I will find a partner. How many choices? 3 choices. Now, once I have found a partner for 2, then I will see how many remaining vertices. In these remaining vertices, I will find what is the minimum numbered vertex, and I will find the partner for that also. Yes or no? So that's it. So finally, the number of perfect matchings, that will be 5 into 3 into 1. Is this clear to everyone? Let me know. So this is the method number 1. Understood? Now let's see method number 2. The same question we can solve using another method, that is method number 2. You already know that in a perfect matching, I need 3 edges. Okay, this you already know, that in a perfect matching, what I need? I need 3 edges. This is, this is, this is. 3 edges I need. So you can see this is a complete graph. So every two vertices are adjacent. The point is that just think about these as 6 people. Okay, let's assume, just think that these are 6 people. We have total 6 people. These are 6 friends. Okay, these are like 6 friends. They are going to a hotel. And this perfect matching, it is like a hotel. So very simple. If 6 friends are going to a hotel, then they must get a room, right? Okay. Okay, and let's assume the capacity of every room is 2, and all the rooms are same. Why all the rooms are same? Because this is a set. So order does not matter. Yes or no? The order does not matter. For example, in this room, if you put 1 2, then 3 4, or if you put 3 4 here, 1 2 here, that does not matter, because it is a set. Correct? So very simple point. In this complete graph, every two vertices are adjacent. Now, what you need to do basically, from these 6 people, from these 6 friends, any two friends you can choose and you can put in this room. Then from the remaining 4 friends, any two friends you can choose and you can put them in this room, and the remaining 2 friends will go to this room. Very simple, right? So which template is this? This is distribution of objects into boxes. 6 friends we need to distribute into 3 rooms. The rooms are identical. What is the reason? Because it is a set. We are finding the set. Set is unordered. The order doesn't matter. Set is unordered. So it is like we need to distribute 6 friends into 3 rooms. These are like 3 boxes or 3 rooms. 3 identical rooms. Okay, because order doesn't matter. So I can say these are like 3 identical rooms. Okay, and every room should get two people. So any two friends you choose, you can put them in this room. From the remaining four friends, you choose two friends and put in this room, and so on. Okay, so which template is this? Distribution of objects into boxes. Which template is this? Anyone? This is distinct objects and identical boxes. Yes or no? Distinct objects, identical boxes. This is DOIB template from the combinatorics. These concepts we have studied in the combinatorics DOIB template. So this is actually DOIB template. I hope you understood. Is this clear? Very simple. We have K6 and the vertices are 1 to 6, 3, 4, 5, 6. And in this K6, we need to find perfect matching. Perfect matching should cover all the vertices, and it is set of edges which are pairwise non-adjacent. So basically 3 edges we need. Okay. Now what we will do, from these 6 people, I can choose 2 people and I can put them here. Okay. From these 6 people, I can say it will be like 6C2. These are the 6 people. I will choose 2 of them, and they are adjacent because this is complete graph. So whatever 2 people I will choose, they are already adjacent. There is edge between them. So I can say that from these 6 people, let me choose 2 people and let me put it here. Okay. Let's assume that I am putting, for a moment, let's assume that I am putting 2, 5 here. Okay. Now remember, I need to do this also, this also. So you can see that from the remaining 4 people, you choose 2 people and you put them here. So remember, we have already got this age 2, 5. Now from the remaining 4 people, you choose 2 people. Let's assume that I'm choosing 1, 6 and you put them here. And then you can see from the remaining 2 people, you choose 2 people and you put them here, 3, 4. That's it. But notice one thing, because this is unordered, because this is a set. Okay. Because this is a set. So in the DOIV template, I told you that you will divide by 3 factorial, because you are putting 2 here, 2 here, 2 here. It's like these 3 rooms are these 3 rooms are identical. And when you have RRR, then you will divide by 3 factorial. In the DOIB template, we have already seen this, if you remember. Okay, because please understand that these two things are same. If I put like this, for example, if I put 2, 5, 1, 6, 3, 4, and if I put 1, 6, 2, 5, 3, 4, or if I put 1, 6, 3, 4, 2, 5, or if I 6, and so on, total 6 will be there, or I can say total 3 factorial will be there. 3 factorial ways, and all these 3 factorial ways, these are same 3 factorial ways, and all of them are basically same. Yes or no? These are basically same. So that is the reason we are dividing by 3 factorial. Did you understand? You can see 2, 5, 1, 6, 3, 4, 1, 6, 2, 5, 3, 4, 1, 6, 3, 4, 2, 5, and so on. Total 3 factorial will be there. You can see. Okay, using these 3, total 3 factorial ways are there. Okay, to order them, I can say. But set is unordered. So all these 6 orders, all these 6 permutations are basically same. Correct? So that is the reason we are dividing by 3 factorial. That's it. I hope you understood. Is this clear? Let me know. So remember, this is the point that we are getting DOIB template. And in the DOIB template, when you have 2, 2, 2 like that, then I told you that we will divide by 3 factorial. This we have already seen in the DOIB template, but I hope you understood why we are dividing by 3 factorial. We are dividing by 3 factorial because these 3, they can arrange in 3 factorial ways, and all those ways will be same. So that is the reason we are dividing by 3 factorial. Okay. Is this clear? Both the method number 1, method number 2. So for this question, what will be the final answer? How many perfect matchings are there in a complete graph on 6 vertices? So you can see what we were doing. From 6 vertices, you can choose 2 vertices. From the remaining 4 vertices, you can choose 2 vertices. From the remaining 2 vertices, you can choose 2 vertices. But the point is, remember that perfect matching, it is a set, so it is unordered, so we will divide by 3 factorial. Okay, so you can calculate this value, this will be your answer. If you calculate this value, it will be 15. So this was our method number 2. This was method 2. And using method 1, what was the answer we were getting? Method 1 using, so we were getting the answer 5 into 3 into 1. 5 partners for 1. Then from the remaining 4 vertices, for the minimum numbered vertex, 3 partners. Then from the remaining 2 vertices, for the minimum numbered vertex, 1 partner. So like that, 15. Okay, for this question, the answer will be option A. I hope you understood. The same question, if they ask you for K8, then how you will do? For K8, if I ask you the same question, let's assume that vertices are 1, 2, 3, 4, 5, 6, 8. Okay. So tell me, for the K8, what will be the answer? Using method 1, what will be the answer? Using method 2, what will be the answer? Method 1. We are making a perfect matching. Perfect matching will cover all the vertices. You have 8 vertices in this K8. So total 4 edges I need. Do you agree with me? In the perfect matching, whatever perfect matching you create, it will contain 4 edges. Every edge will cover 2 vertices. Yes or no? We already know every edge will cover 2 vertices. And no 2 edges can cover any common vertex. Any 2 edges you take, they will cover disjoint vertices. So 4 edges I need to take, and then all the 8 vertices will be covered. So you can see in the perfect matching, total 4 edges will be there. You can see perfect matching will cover all the vertices. So this vertex 1 should be covered. So for this this vertex 1, I need a partner, means I need a edge which will cover vertex 1. I need to choose one of the edge incident on 1. So for 1, how many partners? For this partner, how many choices are there? 7 choices. 7 choices, right? Once I have selected, means for example, let's assume that with this one, let's assume I have selected 4. Okay, with this one, I have chosen 4. Now you can see from the remaining 6 vertices, what are the remaining 6 vertices? These are the remaining 6 vertices. I need to cover these remaining 6 vertices also. So what is the minimum numbered vertex? That is 2. Now let's find the partner for 2, because you need to cover 2. Okay, perfect matching will cover all the vertices, so I need to cover the vertex 2 also. So I need to find a partner for 2 also. Okay, let's find the partner for 2. How many choices for partner for 2? So that will be 5 choices. Okay, I cannot use 1,4 as a partner of 2. Okay, yes or no? So 5 choices for partner of 2. Let's assume as a partner of 2, I have chosen 3. Okay, now you can see how many vertices are remaining. You can see these vertices are remaining. What is the minimum numbered vertex? That is 5. So let's find the partner of 5. So for partner of 5, how many choices are there? 3 choices. Okay, let's assume with 5, I have chosen the partner, that is 8. Okay, now how many vertices are remaining? 2 vertices are remaining. What is the minimum numbered vertex? That is 6. I need to find a partner of 6. How many choices are there? Only 1 choice. So finally, I can say the number of perfect matchings. Number of perfect matchings, that will be 7 into 5 into 3 into 1. This will be your answer. I hope you understood. Clear? Let's see method 2. Method 2. You can see we need a perfect matching. So perfect matching will have 4 edges. Every edge will cover 2 vertices. Total 8 vertices I need to cover. Every edge will cover 2 vertices. And remember, any 2 edges you take, they will cover disjoint vertices. So 4 edges will cover total 8 vertices. 4 edges I need. Okay. Here I need 2 people. Here I need 2 people. Here I need 2 people. And here also 2 people. Correct? Okay. Yes or no? So here I need 2 people. So what I can do for here, from 8 people, I can choose 2 people and I can put them here. Okay. And I need to do this also, this also, this also. So you can see from the 8 people, I can choose 2 people. Let me choose, for example, 4, 7. Okay, from 8 I am choosing 2 people. Then you can see from the remaining 6 I will choose 2. Let's assume from the remaining 6 I am choosing 2, that is 2 8. Then from the remaining 4 I will choose 2 people. Let me assume that I am choosing 1 5. Then from the remaining 2 I will choose 2 people, so that will be 3 6. Okay, that's it. But remember, there is a catch here. What is that? The point is I have to divide by 4 factorial. What is the reason I am dividing by 4 factorial? Because this is a set and it is unordered. So these 4, okay, remember these 4, they can arrange in 4 factorial ways, but all those ways will be same because it is a set. If I arrange these 4 in 4 factorial ways, then all the set that I will get, they will be same set. Set is unordered collection of items. So that is the reason I am dividing by 4 factorial. Okay, I hope you understood. Okay, is this clear? That from here you can see, if you notice, then it will be like 47281536. This arrangement is there. And remember, when you are selecting 2 items from 8 items, maybe you can select 2 8. From the remaining 6, when you are selecting 2 items, maybe you can select 1 5. From the remaining 4, when you are selecting 2, maybe you can select 4 7. And from the remaining 2, you are selecting 2, so you 3 6. The point is that these are actually same. Okay, yes or no? Maybe what you can do like this. The point is like this: total 4 factorial same ways are there, same sets are there. Like this, if you arrange these 4 people, if you arrange them in 4 factorial ways, same sets you are going to get. So like this, 4 factorial same sets you are going to get. Okay, so that is the reason I am saying that you divide by 4 factorial. So that will be your answer. I hope you understood. So remember, this gate 2003 question we have solved. This is asking for number of perfect matchings in case 6, and we have also found the number of perfect matchings in k8. So similarly, you can find number of perfect matchings in any complete graph on even number of vertices. So let's do that generalization also. We have k2n, we have complete graph on 2n vertices, k2n, where n is greater than equal to 1. So if you have a complete graph on even number of vertices, then what will be the number of perfect matchings? Find number of perfect matchings in k to n. So let's find it. Again, there are 2 ways: way 1, way 2, method 1, method 2. So let's see method 1. In method 1, first you assume that the vertices are 1, 2, 3, and so on to n. These are the vertices. Okay. Now, what is the method 1? Remember just how we did for k6, for k8. Similarly, you can do for k2n. In the method 1, what you will do? You already know that in this perfect matching, see, we are creating a perfect matching. In this perfect matching, you already know that how many edges will be there. Can anyone tell me? Total 2n vertices we have. Every edge will cover 2 vertices. We need to cover all the vertices, and every 2 edges will cover disjoint vertices. So tell me, in this perfect matching, how many edges will be there? Exactly n. Yes or no? In this perfect matching, there will be n edges. Okay, there will be total n edges, remember. So because this perfect matching will cover all the vertices, so vertex 1 also should be covered. Now, for vertex 1, I need to take one edge which will cover vertex 1. Okay, remember this is complete graph. So every 2 vertices are adjacent. Now you can see, to cover this vertex 1, I need a partner of 1. I need a edge which will cover vertex 1. I need a edge which is incident on vertex 1. So tell me, as the partner of vertex 1, How many choices I have? For partner of vertex 1, how many choices I have? I have 2n minus 1 choices. Yes or no? 2n minus 1 choices. Very good. Very simple. Now you tell me, let's assume that with this one, I have already chosen a partner. Okay, a partner I have already chosen. Then what I will do? Then from the remaining 2n minus 2 vertices, I will find the minimum numbered vertex, and for that I will find partner. Yes or no? See, notice one thing. With this one, I need a partner. There are 2n minus 1 choices. Let's assume I have chosen the partner 4. This partner 4 I have chosen. Now, how many vertices are remaining? 2n minus 2. In those vertices, who is the minimum numbered vertex? That is 2. For this 2, I need a partner. Correct? Now, for this 2, as a partner, how many choices are there? So, as a partner, I cannot choose 1. As a partner, I cannot choose 4. So, as a partner, 2n minus 3 choices are there. Okay, because remaining how many vertices are there? 2n minus 2. And for this 2, how many partner choices are there? That is 2n minus 3. Is this clear? Let's assume that for this 2, I have chosen a partner that is 3. Now, how many vertices are remaining? 2n minus 4. In those vertices, who is the minimum numbered vertex? That is 5. I will find a partner for 5. How many choices are there? Remember, total 2n minus 4 vertices are there. With this 5, how many partner choices are there? That will be 2n minus 5. Remember, after this 1, 4, 2, 3, 2n minus 4 vertices are remaining. Now, in these 2n minus 4 vertices, for vertex 5 as a partner, how many choices are there? That will be 2n minus 5. So, like that, 2n minus 5 choices will be there. Now, for this 5 also, you will find a partner. Let's assume that is 8. Okay, this is the idea. I hope you understood. So, you can see that the sequence will be like this, that 2n minus 1 multiplied by 2n minus 3 multiplied by 2n minus 5, and so on. At the end, there will be only one choice. Yes or no? At the end, there will be only one choice. So, the number of perfect matchings, what that will be? The number of perfect matchings in K2n. In K2n, what that will be? That will be 2n minus 1 multiplied by 2n minus 3 multiplied by 2n minus 5, and so on, 1. Okay, like this. Okay, so this is the number of perfect matchings in K2n. I hope you understood. Actually, there is method number 2 also, that is recurrence relation we can write. We can write recurrence relation. Think recursively. Can you think recursively? I told you in the beginning of this lecture, in the previous lecture also, I told you that whenever the question ask you to find the number of matchings, the number of perfect matchings, the number of independent sets, and so on, always think recursively. So, can you think recursively? Very easily you can think. Notice one thing. We already know that in the perfect matching, total n edges will be there, and perfect matching should cover all the vertices. So the vertex 1 also should be covered. Vertex 1 should be covered. So with vertex 1, I need a partner. Basically, I need a edge which will cover vertex 1. I need a edge which is incident on vertex 1. Okay. So just focus on this vertex 1. When you are thinking recursively, focus here. Focus on vertex 1. Okay, focus on vertex 1. So when you are thinking recursively, just focus on vertex 1. Now, for vertex 1, I need a partner. how many choices are there for partner of vertex 1? 2n minus 1 choices. Yes or no? 2n minus 1 choices. Now notice, for this one, let's assume that I have chosen the partner 2 or maybe 3. Let's assume you have chosen the partner 3. Now, how many vertices are remaining? 2n minus 2. So, you will create a perfect matching in k2n minus 2. Do you agree with me? Did you understand that? I am saying for this vertex 1, just focus on this vertex 1. I need to cover vertex 1. So, I need a edge which is incident on 1. So, you can see to cover this vertex 1, I need a partner of 1. As a partner of 1, there are 2n minus 1 choices. Now, you can see after that, how many vertices are remaining? Here, what I need. Just tell me here what I need. Here, I need a perfect matching in remaining 2n minus 2 vertices. Yes or no? Here you need to find a perfect matching. You need to find a perfect matching among remaining 2n minus 2 vertices. Okay, do you agree with me? Remember, you need to do this also and you need to do this also. Okay, means this work also you need to do and this work also you need to do. So there is a and here. So and means multiplication. Okay, so what I'm trying to tell you that just think recursively. The vertices are 1, 2, 3, and so on 2n. These are the vertices. We have complete graph on 2n vertices. We are thinking recursively. Okay, thinking recursively. We are thinking recursively, and for a moment assume that Sn, this is the number of perfect matchings in this is the number of perfect matchings in k2n. Okay, or I can say s2n. What is s2n? S2n is the number of perfect matchings in k2n. Is this clear? In this complete graph on 2n vertices, the number of perfect matching I am denoting by s2n. So what this s2n will be? What this s2n will be? This will be equal to, think recursively. We are thinking recursively. You can see to cover the vertex 1, just focus on 1. Okay, you can see this should be your focus. So focus on this vertex 1. For this vertex 1, how many choices are there as a partner? That is 2n minus 1. Okay, yes or no? You need a partner for 1, and then you need a perfect matching among the remaining 2n minus 2 vertices. Yes or no? So you need to do this task also, you need to do this task also. So you can see multiplied by. Now, for the remaining 2n minus 2 vertices, I need a perfect matching. So tell me, for the remaining 2n minus 2 vertices, how many perfect matchings are there? That will be as 2n minus 2. That's it. Okay, so this is how you can think recursively. Did you understand? We are thinking recursively. Just focus on this vertex 1. For this vertex 1, you find a partner. So there are 2n minus 1 choices. After that, there are 2n minus 2 vertices remaining. And in those 2n minus 2 vertices, you among those 2n minus 2 vertices, you need to find a perfect matching. So the number of perfect matchings in among the remaining 2n minus 2 vertices, that will be as 2n minus 2. Okay, yes or no? I hope you understood. So remember, you need to cover vertex 1 also, and you need to find perfect matching among the remaining 2n minus 2 vertices also. That is the reason we are doing this multiplication. Okay, that's it. So s2n is equal to 2n minus 1 into s2n minus 2. Tell me, this recurrence relation will work when the value of 2n this should be greater than equal to what? You can see the value of the value of n, just focus on, or maybe 2n, no problem. So means the number of vertices. So tell me the number of vertices should be what? If I put the number of vertices equal to 2, then it will be like S0. Okay. We don't have S0, right? We don't have complete graph on 0 vertices. Every graph must have at least one vertex. Okay. So you can see 2n should be greater than equal to 4. Okay. Basically, this recurrence relation will work when 2n is greater than equal to 4 or n is greater than equal to 2. Okay. The point is where 2n is greater than equal to 4. Where 2n is greater than equal to 4. That's it. Okay. So this is the recurrence relation we got. I hope you understood. So find the number of perfect matchings. Let me just write the recurrence relation. So let's assume that S2n, this is the number of perfect matchings in K2n. Then we have found that S2n, this is equal to 2n minus 1 multiplied by S2n minus 2. Okay. Where 2n is greater than equal to 4. What are the base cases? What are the base cases? Base case is S2. Okay. S2 means basically K2. That will be your base case. K2. K2 means complete graph on 2 vertices. So tell me what will be S2. That you can find manually. The base cases. S2 means the number of perfect matchings in K2. How many perfect matchings are there in this K2? There is only one perfect matching. Okay. So that's it. Now you can easily find what will be S4. So what that will be? Tell me. You can see here. Let me write it here. What will be S4? S4 will be equal to what? Tell me. S4 will be equal to, remember here 2n is the number of vertices. So here number of vertices is 4. So you can see that will be 3 into S2. 3 into S2. Okay, yes or no? 3 into S2. You can see S2 is 1. So that will be 3. You can easily find what will be S6. S6 will be 5 into S4. 5 into S4, that will be 15. Okay, and this was your gate question. Yes or no? Is this clear? What will be S8? That will be 7 into S6. So remember, S8 will be 7 into S6, 7 into 15. What will be S10? If you have complete graph on 10 vertices, then what will be number of perfect matchings? That will be 9 into S8. Okay, so like that. I hope you understood. So we have seen there are two general methods. Two methods we have seen. One is thinking recursively. Another method we have seen where we got a formula. And let me just tell you one more method, method 3 also, that is DOIB template, right? Okay, so let's just see this method 3 also quickly. Basically, for K2n, let's assume that vertices are 1, 2, 3, 4, and so on. 2n, these are the vertices. And we need to find number of perfect matchings in K2n. Okay, then what that will be? So just let's apply our method 3. What was method 3? That was basically our DOIB template, right? That we were discussing about when we were discussing for K6, K8. Okay, so what you can do here, very simple. You already know that in a perfect matching will cover all the vertices. To cover 2n vertices, in the perfect matching you need total n edges, because every edge will cover two vertices, and any two different edges will cover disjoint vertices. Yes or no? Total n edges I need. So very simple. From these two n people, you choose two people and you put that edge here. Means from the two n people you choose two people. Then and what you need to do, from the remaining 2n minus 2 people you choose two people and you put them here. Correct? Okay, and so on. You can see from the remaining 2n minus 4 people you choose two people and you put them here, and so on. At the end, from the two people, choose two people and you put them here. Okay, but remember, we need to divide by what? If you remember, I told you we need to divide by n factorial, because total we have n edges. So these n edges I can order in n factorial ways, and all those n factorial ways will describe the same set. They will describe the same perfect matching. Yes or no? Is this clear? These are total n factor and these are total n edges. I can arrange them. I can order them in n factorial ways, and all those will be same perfect matchings. All those will describe the same set, because perfect matching is a set of edges. Set is unordered. So you can see we will get number of perfect matchings. Number of perfect matchings is equal to this formula. Now let's open this formula. So remember, in K2n, the number of perfect matchings, that is equal to, from 2n vertices you choose two vertices, that edge you put. From the remaining 2n minus 2 vertices you choose two vertices, that edge you put. From the remaining 2n minus 4 vertices you choose two vertices, that edge you put. From at the end 2c2, and divide this whole thing by n factorial. The reason I told you, because these n edges, if I arrange them, then total n factorial arrangements are there. All those arrangements describe the same set, because set is unordered collection of items. So all those n factorial orders, all those n factorial arrangements, they will describe the same perfect matching. So we are dividing by n factorial. Now if you simplify it, what you are going to get, let me tell you. Just simplify it. You can see you will get 2n into 2n minus 1 divided by 2 factorial. Then 2n minus 2 into 2n minus 3 divided by 2 factorial, into 2n minus 4, 2n minus 5 divided by 2 factorial, and so on, and so on. You just keep going. 2 into 1 divided by 2 factorial. Okay, and this whole thing is divided by n factorial. Correct? Now you can notice one thing. What you can do, you can take 2 see, here you can take 2 out, here you can take 2 out. Okay, then what you will get, this 2 you take it out. From here you off, here also you take 2 out. Are you getting my point? From here also, just see, this 2 you take it out, and from here also you take 2 out. Okay, from here also you take 2 out, and from here also you take 2 out. So tell me, this first component, it will give you 2 power n, because total we have n like this. Okay, total we have, these are total n items actually. Okay, because there were n edges in the perfect matching, right? So these are basically total n items. Now you can see we will get 2 power n. Then the remaining, that will become n into n minus 1 into n minus 2. So that will become n factorial. Yes or no? And in the division, what we have? In the division, we have 2 power n. In the division, we have 2 power n. In the division, we have n factorial also. Then what remains? This second component remains. What this second component? This second component. what this second component will be. That will be 2n minus 1, 2n minus 3, 2n minus 5, and so on. At the end, 1. Okay. You can see this will cancel out. It will cancel, it will cancel. So finally, the number of perfect matchings that you will get, that will become 2n minus 1 into 2n minus 3 into 2n minus 5, and so on. Just keep going on till 1. This is your number of perfect matchings in complete graph on 2n vertices. Okay, let me just give you one example. In K10 or in K12, maybe K10. Okay, in K10, what will be the number of perfect matchings? In K10, that will be 9 into 7 into 5 into 3 into 1. This will be the number of perfect matchings in K10. Okay, that's it. I hope you understood the complete analysis of this GATE 2003 question. You can read my answer that I have written on GATE overflow under this GATE question. You can see under the GATE 2003 question, this detailed answer I have written, where I have found the recursive formula for number of perfect matchings in complete graph on 2n vertices. This was the recursive formula. The reason also I have written, the explanation I have written. Okay. So basically everything, the complete analysis of this GATE 2003 question that we have done, you can read here also. You can see this answer I have written. And some variations also I have written here. So let's discuss these variations. You can see on the GATE overflow, I just have written these 4 questions, but I did not provide the answer. Let me provide you the answer now. You can pause the video and you can think about these variations. Number of maximal matchings in K2n, number of maximum matchings in K2n, number of maximal matchings in K2n plus 1, number of maximum matchings in K2n plus 1. You can pause the video, you can think about it. These 4 questions. Let me give you the answer. So let's see the answer for these 4 variations. First, we have already seen that in K2n, first let's talk about perfect matchings. Okay. First, let me talk about number of perfect matchings. Okay. So let's discuss the number of perfect matchings. This actually we have already seen that if you have K2n, then what will be number of perfect matchings? The number of perfect matchings that we have already found, that was 2n minus 1 multiplied by 2n minus 3 multiplied by 2n minus 5, and so on till 1. Correct? Okay. So this actually we have found. For example, if I find for K6, what will be the number of perfect matchings? Then that will be 5 multiplied by 3 multiplied by 1. That will be 15. Okay, very simple. Now you tell me, if you have complete graph on odd number of vertices, K2m plus 1, tell me complete graph on odd number of vertices. This is basically same as complete graph on odd number of vertices. Then tell me what will be the number of perfect matchings? That will be 0, because if your graph has odd number of vertices, then there will be no perfect matching. Yes or no? This actually we have already seen in our lectures, that if you have graph with odd number of vertices, with odd number of vertices, if you have graph with odd number of vertices, then it implies that there is no perfect matching exist. No perfect matching exists. Okay, but remember, if you have graph with even number of vertices, if you have graph with even number of vertices, then in a graph with even number of vertices, perfect matching may or may not exist. It will depend on the graph. Perfect matching may or may not exist. Okay, is this clear? Very simple. It will depend on the graph. So you can see, if you have complete graph on odd number of vertices, number of perfect matchings will be 0. But if you have complete graph on even number of vertices, then the number of perfect matchings we have already found. Now let's discuss the number of maximal matchings, the number of maximum matchings in K2n and also in K2n plus 1. Means in complete graph on odd number of vertices, in complete graph on even number of vertices. So just tell me a simple point. In K2n, means complete graph on even number of vertices, what do you think? Is it possible that a maximal matching is not perfect? Is it possible? Can you create a maximal matching which is not perfect? Tell me, in this graph, can a maximal matching, can a maximal matching, can a maximal matching not be perfect in this graph? In general, we know. Okay, I'm not asking the general case. Remember, we already know, not that in general, in general, first let me discuss the general case. In general, in a graph G, in a graph G, we already know that maximal matching does not imply maximum matching. Means maximal matching may not be maximum. We also know that maximum matching does not imply perfect matching. Remember, every perfect matching is maximum and every maximum matching is maximal, whatever graph you take. Okay, let me give you a counter example. Basically, let me give you a graph where maximum matching is actually not perfect matching. Also, we have even number of vertices. Okay, let me give you this. Consider this graph. Let's assume we have vertex A, B, C, D. You can notice here we have even number of vertices. The number of vertices is actually even. Okay, but here, if you notice, what is the maximum matching you can create? What is the largest matching that I can create? The largest matching will have single edge, because in this graph every two edges are adjacent. Every two edges have a common endpoint A. So in this graph actually there is no perfect matching. Yes or no? Okay, so you can notice maximum matching may not be perfect. You can see maximum matching does not mean it is perfect. So maximum matching may not be perfect. If you have even number of vertices, then also maximum matching does not mean it is perfect. Okay, so very simple. But let's talk about complete graph. For complete graph, can a maximal matching not be perfect? Is it possible that there is a maximal matching which is not perfect? The answer is no. The answer is no. Every maximal matching actually will be perfect. You can easily prove it by contradiction. If a maximal matching is not perfect, let's assume, see, you can prove by contradiction. You can prove by contradiction. How to prove by contradiction? Let's assume that there is a maximal matching. Let's assume there is a maximal matching. You have this complete graph on 2n vertices. Let's assume these are the vertices 1, 2, 3, and so on 2n. Okay. Now, for a moment, assume there is a maximal matching, and let's assume that maximal matching covers this maximal matching. Let's assume this covers only 2n minus 2 vertices. Okay, see, these are the vertices 2n minus 2, 2n minus 1, and 2n. These are the total 2n vertices, right? Now, for a moment, assume that there is a maximal matching. This maximal matching, let's assume this covers 2n minus 2 vertices. 2n minus 2 vertices means these vertices are covered. For a moment, assume that, let's assume these vertices are covered. These vertices are not covered. Okay. Now you can notice this is not maximal because this is a complete graph. So every two vertices are adjacent. So whatever two vertices you did not cover in this maximal matching, those actually also we can cover. Yes or no? Did you understand? Very simple. Remember, the graph is complete graph. So every two vertices are adjacent. Now, if you create a maximal matching which does not cover all the vertices, it is guaranteed that it will cover even number of vertices, right? Yes or no? We already know that every matching will cover even number of vertices. If you have matching of size k, then it will cover 2k vertices. 2k unique distinct vertices it will cover. If you have matching of size 10, it will cover 20 distinct unique vertices. Every matching of size k covers 2k unique distinct vertices. Okay, so if you assume that this maximal matching does not cover all the vertices, then definitely this will cover even number of vertices. If it is covering even number of vertices, then you can notice this is not maximal because the remaining two vertices, these are also adjacent and these are not covered by this matching. And I can add this edge here. Yes or no? I can make this matching bigger. So definitely it is not maximal. I hope you understood. Okay, is this clear? So you can notice that I can add this edge. In this, I can add this edge 2n minus 1, 2n minus 2. Okay, this edge I can add. And that is the reason there is a contradiction. Yes or no? So I can add this edge. So that is the reason this is not maximal, contradiction. So I can say that every maximal matching is perfect in this complete graph on 2n vertices. Okay, so can you have a maximal matching which is not perfect? The answer is no. So finally I can say that in this k2n, notice that every maximal matching is perfect. Here if you create a maximal matching, every maximal matching is perfect. Okay, so that's it. Every perfect matching is already maximal. Every maximal is perfect. Similarly, here you can see that every maximum matching is also perfect. In this, every maximum in this complete graph I am talking about. If the graph is not complete, then a maximal matching may or may not be perfect. A maximal matching may or may not be maximum. A maximum matching may or may not be perfect in a general graph. But in a complete graph, every two vertices are adjacent. So every maximal matching is perfect. Every maximum matching is also perfect. Okay, so you can see in this k2n, you can see the number of maximal matchings will be equal to number of maximum matchings and that will be equal to number of perfect matchings. I hope you understood. Very simple, right? Now, what about k2n plus 1? Means complete graph on odd number of vertices. k2n plus 1. What can you say about this graph? Very simple. Number of perfect matching will be 0, right? Yes or no? number of perfect matchings will be 0, means no perfect matching exists. Very easy. And what about number of maximum matchings? Tell me here, what will be number of maximum matchings? You can see that every matching will cover even number of vertices, that you already know. Okay, that we already know that every matching covers even number of vertices, whatever matching you take. Because remember, in a matching you have edges, pairwise non-adjacent edges. So every edge will cover two vertices, and every two edges are non-adjacent, so they will cover disjoint vertices. So I can say if you have k edges, then 2k unique distinct vertices will be covered. Okay, so every matching will cover even number of vertices. So you can see, if every matching is covering even number of vertices, then whatever maximum matching I will create, that will also cover even number of vertices. So definitely maximum 2n vertices I can cover. Do you agree with me? For example, if you have complete graph on 11 vertices, then any maximum matching that I will create, that can cover maximum 10 vertices. Yes or no? Maximum 10 vertices we can cover here. I hope you understood. So number of maximum matchings in k2n plus 1, that will be equal to, remember, one vertex will be left, because maximum 2n vertices we can cover, one vertex will be left. So first you decide which vertex is left. Total we have 2n plus 1 vertices, one of them will be left. So 2n plus 1 choices are there for the left vertex, left out vertex. Yes or no? For the left out vertex, 2n plus 1 choices are there. Then in the, for the remaining 2n vertices, you can create maximum matching. And you can see, we have already seen that if you have complete graph on even number of vertices, then number of maximum matchings will be same as number of perfect matchings. So you can see that in this remaining is k2n, so that will have number of perfect matchings in k2n. Okay, so basically what you will be getting, remember something interesting. So the maximum matchings number of maximum matchings in k2n plus 1, that will be equal to, that will be equal to, you can see that will be equal to 2n plus 1 for the left out vertex, correct, multiplied by, in the remaining k2n, in the remaining 2n vertices, you need to create maximum matching, and that will be a perfect matching. So how many perfect matchings are there in k2n? That we already know, 2n minus 1 into 2n minus 3 and so on into 1. So this quite interesting result we got, right? Yes or no? That's it. Very simple. And the same thing will work if I ask you for number of maximal matching in k2n plus 1. Because again the same thing, every matching will cover even number of vertices. So in this k2n plus 1, maximum how many vertices I can cover, that will be 2n, correct. So you can see one vertex will be left out. So first you find that vertex which is left out, then in the remaining 2n vertices you create maximal matching, and in a complete graph on even number of vertices, every maximal matching is perfect matching, every perfect matching is maximal. So you find number of perfect matching in k2n. So you can see that the same formula you will get if I ask you the number of maximal matchings in k2n plus 1. That's it. These are the variations and we have seen the answers. I hope you understood. So these were the four variations that I was asking. Number of maximal matchings in K to N, number of maximum matchings in K to N. So these two, these will be equal to number of perfect matchings in K to N, that we have already found. That we have already found the number of perfect matchings in K to N, that is equal to 2n minus 1, 2n minus 3, and so on 1. Okay. And these two questions also we have found the answer. Number of maximal matchings in K2n plus 1, number of maximum matchings in K2n plus 1, that will be equal to 2n plus 1 for the left out vertex. This is for, this is the left out vertex, right? Left out vertex multiplied by number of perfect matchings in K2n. Okay, that's it. That's it. Easy peasy. I hope you understood. Let's solve GATE 2026 question. Let GVE be a simple undirected graph. A vertex cover of G is a subset of vertices such that every edge has at least one endpoint in this subset. Okay, so this is the definition of vertex cover. I told you vertex cover is a subset of vertices which will cover all the edges. Means for every edge, at least one of its endpoint must be there in the vertex cover. Yes or no? We have already seen that for every edge of the graph, at least one of the endpoint of that edge must be present in vertex cover. Okay, very simple. So this is given to you that a vertex cover is subset of vertices such that every edge has at least one of its endpoints in the vertex cover. Okay, so this is the definition of vertex cover. Very simple. Now the question is saying, let the size of smallest vertex cover be k. So vertex cover number is k here. Smallest vertex cover means minimum vertex cover. So the vertex cover number, that is k. Let S be any vertex cover of size k. So what is S? This is vertex cover of size k. And what is k? This is the size of smallest vertex cover. So I can say S is a smallest vertex cover. Remember, in any graph, smallest vertex cover may not be unique, but all the smallest vertex covers will have the same size. Okay, remember, minimum vertex cover, or I can say smallest vertex cover, it may not be unique, but all the minimum vertex covers, or I can say all the smallest vertex covers will have same size. So from these two lines, you can see that S is a smallest vertex cover. Okay, so you can see, first of all, from this line I can say that vertex cover number, that is beta. What is beta? This is the vertex cover number, vertex covering number, that is k. Okay, what is vertex cover number? That is the size of smallest vertex cover. And you can see S is any vertex cover of size k. From here I can say that S is a smallest vertex cover. S can be any smallest vertex cover, remember. S is a smallest vertex cover. Now the question is asking, for a vertex V, which of the following condition will always ensure that V belongs to smallest vertex cover? And remember, this S can be any smallest vertex cover. Yes or no? This S can be, this S is any smallest vertex cover. Any. Okay, so let me write it here that this S is any smallest vertex cover. So what this question is asking, it is asking that for a vertex V, which of the following conditions will always ensure that V belongs to S, where S is any smallest vertex cover. So which of them will guarantee that vertex V will belong to all the smallest vertex covers? Because S can be any smallest vertex cover. and we need to guarantee that V belongs to S, and S can be any smallest vertex cover. So we need to guarantee that this V belongs to all the smallest vertex covers. Okay, so remember, basically this what it means. It means that V belongs to all smallest vertex covers. Whatever smallest vertex cover you create, all smallest vertex covers. All smallest vertex covers. I hope you understood. See, the language of this question is not easy to understand, but if you just think about it step by step, then you can easily understand. Just notice here that K is the size of smallest vertex cover. So K is the vertex cover number. Now S is any vertex cover of size K. Now remember, S can be any vertex cover of size K, means S can be any smallest vertex cover. S can be any smallest vertex cover. If S can be any smallest vertex cover, and the question is asking that for a vertex V, which of the following condition will guarantee that always ensure that this vertex V belongs to S, but this S can be any smallest vertex cover, and we want to guarantee that always this V should belong to S. It means that this V should belong to all the smallest vertex covers. Okay, this V should belong to all the smallest vertex covers. I hope you understood. So the question is basically asking, so the question is asking, so the question is asking which condition, which condition ensures that a vertex V, a vertex V always belongs to all smallest vertex covers. Vertex covers of the graph. Okay, is this clear? The question is asking which condition ensures that a vertex V always belongs to all smallest vertex covers of the graph. Understood? Now let's see all these options one by one. Let's see the first option. The degree of V is at least K plus 1. We will try to counter it. We will try to contradict it. Means we will try to find a contradiction. And if we cannot counter it, then it means that this is true. Do you agree with me? See, let's see option A. Option A is saying that vertex V, degree of V, degree of V is at least K plus 1. Degree of V is greater than equal to K plus 1. Okay, and remember what is K here? What is K here? This is size of smallest vertex cover. Size of smallest vertex cover in graph G. And the option A is saying that degree of V is greater than equal to K plus 1. Here, notice, for a moment assume that this vertex V does not belong to a smallest vertex cover. Just assume for a moment. Okay, see, you have this vertex V, and this has degree at least K plus 1. Means this is adjacent to at least K plus 1 vertices. Okay, let's zoom A1, A2, A3, A4, and so on, and so on, A, K plus 1. Do you agree with me that this vertex V, this is adjacent to at least K plus 1 vertices? Now remember, vertex cover means we should cover all the edges. Vertex cover means we should cover all edges. Okay. Now, for a moment, assume that this vertex V does not belong to smallest vertex cover. Okay. For a moment, I am just assuming. Okay. For contradiction, assume. For contradiction, For contradiction, assume this V does not belong to a smallest vertex cover. A smallest vertex cover. Okay, this V does not belong to some smallest vertex cover. Now, what will happen? If this V does not belong to some smallest vertex cover, then how to cover this edge? V does not belong to smallest vertex cover. Means there is a vertex cover S which is smallest and this V does not belong to that. Then you tell me one thing. I need to cover all the edges. If this V does not belong to the vertex cover, then how to cover this edge? Just tell me. Simple question I'm asking. If this V does not belong to a vertex cover, there is a vertex cover which is smallest vertex cover and V does not belong to it. Okay. Then how to cover this edge? Tell me. See, this is a smallest vertex cover. This is a smallest vertex cover. This is the smallest vertex cover. And I am saying that this V does not belong to it. V does not belong to it. Then you tell me how to cover this edge. To cover this edge, definitely this AK plus 1 I have to take. Yes. How to cover this edge? To cover this edge, A1 I have to take. Correct? Okay, yes or no? A1 I have to take. Guaranteed, because I need to cover all the edges. Vertex cover will cover all the edges. How to cover this edge? Definitely A1 I have to take. Okay, next you can see how to cover this edge. This edge, how to cover? Definitely A2 I have to take. And so on. And so on. You can see how to cover this edge. Definitely A3 I have to take. How to cover this edge? Definitely A4 I have to take. So, did you notice that? What will be the size of this smallest vertex cover? What will be the size here? That will be at least K plus 1. Do you agree with me? Size will become at least K plus 1. Yes or no? To cover all these edges, at least these K plus 1 vertices I need to take. So the size will become at least K plus 1. This is contradiction because size of smallest vertex cover, that is K. And remember, all the smallest vertex cover have the same size. I told you. Remember, smallest vertex cover may not be unique. You can have many smallest vertex covers, but all the smallest vertex covers must have same size. So here, did you find a contradiction that the smallest vertex cover size is actually K, but here you can see this smallest vertex size, it is greater than equal to K plus 1. So definitely there is a contradiction. Yes or no? A big contradiction we got. So we got a contradiction. We got a contradiction. If we got a contradiction, then our assumption was wrong. What was our assumption? Our assumption was that this vertex does not belong to a smallest vertex cover. So this assumption was wrong. So I can say that this vertex will definitely belong to every smallest vertex cover. Is this clear? So this is what I am saying, that this contradiction. So this is what I am saying, that this assumption leads to contradiction. This assumption leads to contradiction. Okay, if this assumption leads to contradiction, then this assumption is false. And this assumption is saying that this V does not belong to a smallest vertex cover. So this assumption is false. So this V must belong to every smallest vertex cover. Okay, is this clear? So I can say that, definitely I can say that, so such V, so I can say that such vertex V must belong to every smallest vertex cover. It must belong to every smallest vertex cover. Okay, that's it. I hope you understood. So remember, in this question, which of the following condition will always guarantee that vertex V will belong to every smallest vertex cover? So yes, option A, this condition will guarantee that this vertex V belongs to every smallest vertex cover. Okay. What about option B, C, D? For these option B, C, D, you can easily find counter example. Very easy. See, see the counter example for option B. Option B is saying that vertex V is on a path of length k plus 1. So what you do? Just take a path of length k plus 1. For option B, let me give you the counter example. The counter examples are so easy. See, the counter example I can give you. What you do? You take a path of length k plus 1. Means consider this graph. Let's assume that your graph is a P4. Means you have path graph on 4 vertices. This is your path graph. Tell me what is the smallest vertex cover size here? Tell me what is the size of smallest vertex cover? Size of any smallest vertex cover? What that will be? All the smallest vertex covers have same size, remember? So size of any smallest vertex cover, what that will be? That will be 2. This is your value of k. Because what was k? K was size of smallest vertex cover. So remember, for this graph G, you can see for this graph G, the value of k is 2. Okay. Now you tell me, this vertex 1, this is on a path of length k plus 1. Yes or no? Here you can see this is path of length k plus 1. Did you notice? This is path of length k plus 1. Path of length k plus 1 means this is path of length 3. Yes, this is path of length 3. Correct? There are 3 edges. So this is path of length 3. Okay. Now, this vertex 1, this is also on path of length 3. This vertex 2, this is also on path of length 3. This vertex 3 also is on path of length 3, and this vertex 4 is also on path of length k plus 1. But now you can notice that, can I guarantee that this vertex 2 will belong to every smallest vertex cover? No, I can easily give you different smallest vertex covers. For example, let me give you, I can give you smallest vertex covers. Let me give you smallest vertex covers. Okay. For example, these are the smallest vertex cover. Like what I can do, I can take 1,3. This will be a smallest vertex cover. I can take 2,4. This will be a smallest vertex cover. Okay, yes or no? I can take 2, 3. This will be a smallest vertex cover. That's it. I hope you are getting the point. I am saying that you can see that this vertex 1, this is on a path of length k plus 1. But you can see this does not belong to this smallest vertex cover. This vertex 2, this is on a path of length k plus 1. But this does not belong to this smallest vertex cover. This vertex 3 is on path of length k plus 1. But this does not belong to this smallest vertex cover. And this vertex 4, this is on path of length k plus 1. This does not belong to this smallest vertex cover. So you can see option B is saying that vertex V is on path of length k plus 1. But this does not guarantee, this does not always ensure that V will belong to all the smallest vertex covers. Yes or no? Is this clear? So option B does not always ensure that V will belong to all the smallest vertex covers. Okay, is this clear? So I can say that option B is false. We have found the counter example, and the counter example is so easy. You just take the path of length k plus 1. You just take P4. Okay, yes or no? Very easy, so easy. The option itself is telling you the counter example. For example, in option C, what you do, you take cycle of length k plus 1. That itself will be your counter example. Okay, let me tell you option C counter example. Option C counter example, let me tell you. You can see for option C, you just take this cycle. Okay, what is this? This is your graph G, and this is cycle on 3 vertices. Okay, You can see option C is saying vertex V is on a cycle of length k plus 1. Okay. Now you consider this cycle, it has length k plus 1. You can see what is k here. For this G, what will be size of any smallest vertex cover? Size of any smallest vertex cover. So size of any smallest vertex cover, that actually will be 2. At least 2 vertices you need in the vertex cover, and in the smallest vertex cover 2 vertices you need. Yes or no? I can take this A, B, C. So you can see that the value of k is 2 for this graph. For this graph, the value of k is actually 2. And this graph is basically a cycle of length k plus 1. Yes or no? This is cycle of length 3. This is cycle of length 3. Here you can notice what are the smallest vertex covers. What are the smallest vertex covers? So you can see these are the smallest vertex covers. I can take AB, that will be smallest vertex cover. I can take AC, that is smallest vertex cover. I can take BC, that is smallest vertex cover. Okay. Now you can notice this vertex A. This is on a cycle of length k plus 1, but this does not belong to this smallest vertex cover. This vertex B, this is on a cycle of length k plus 1, but this does not belong to this smallest vertex cover. And this cycle C, this is on a cycle of length k plus 1, but this does not belong to this smallest vertex cover. So option C is saying that the vertex V is on cycle of length k plus 1, but this does not always ensure, this does not guarantee that V will always belong to all the smallest vertex covers. Yes or no? So option C, that is also false. The counter example is this C3. Very easy counter example. The option itself is telling you the counter example. Now let's see option D. The vertex V is part of a clique of size k. For this option D also, you can easily find a counter example. What this option D is saying? This is saying that V belongs to a clique of size k. Of size k. Okay, this is option D. And remember, what is k in the question? In the question, what is k? K is size of smallest vertex cover. K is size of smallest vertex cover. Okay, so here for option D also, very easy counter example you can give. What to do? You just take a clique you consider. See, let me consider this. Let assume that this G is K4. Assume your graph G is K4. This K4. This is your graph A, B, C, D. Okay. Now you can notice for this graph, what is the K? Means what is the size of smallest vertex cover? Tell me for this complete graph K4. This is your graph G. What is the size of smallest vertex cover? Can you tell me? Size of smallest vertex cover. This is complete graph on 4 vertices. Every 2 vertices are adjacent. So I need to take at least 3 vertices to cover all the edges. And the size of smallest vertex cover, that will be 3. That will be 3. For example, this is a vertex cover. I can say this is a smallest vertex cover. This is a smallest vertex cover. You can take, this is a smallest vertex cover. Okay, basically any 3 vertices you can take. Okay, any 3 vertices you can take, that will be a smallest vertex cover. Now, so the value of k, that is actually 3. For this graph, the value of k is 3. Now what option D is saying? Option D is saying that vertex V belongs to a clique of size k. Tell me, this vertex A, does it belong to a clique of size k? K is 3. This vertex A, does it belong to clique of size 3? This is simple question I am asking. Look at this vertex A and tell me, does it belong to a clique of size 3? Yes, this belongs to a clique of size 3. Okay, you can see this is clique of size 3. Notice, isn't it clique of size 3? Clique is complete subgraph. This is your complete subgraph K3. Clique means complete subgraph. Clique means complete subgraph. This is your complete subgraph K3. So A belongs to a clique of size 3. C also belongs to a clique of size 3. D also belongs to a clique of size 3. B also belongs to a clique of size 3. Look at this. Look at this. You can see that here A also belongs to clique of size 3. B, C, D, all of them, they belong to clique of size 3. Now, in this graph, what are the smallest vertex covers? What are the smallest vertex covers in this graph? Can you tell me? You can see that if I take ABC, that is the smallest vertex cover. If I take ABD, that is the smallest vertex cover. If I take BCD, that is the smallest vertex cover. If I take ACD, that is the smallest vertex cover. Okay, these are the smallest vertex covers. Now notice one thing. This vertex A, this belongs to a clique of size 3. You can see this is a clique of size 3. So this vertex A belongs to a clique of size 3, but you can see this vertex A is not present in this smallest vertex cover. Similarly, this vertex B also belongs to a clique of size 3, but this vertex B is not in this smallest vertex cover. This vertex C belongs to a clique of size 3, but this vertex C is not in this smallest vertex cover. Similarly, for D also, this vertex D belongs to a clique of size 3, but this vertex D is not in this smallest vertex cover. So option D is saying that V is a part of clique of size K. It does not always ensure that this vertex will always belong to all the smallest vertex cover, right? So for option D also we have seen the counter example. So finally the answer will be only option A. This is actually MSQ question, multi select question, and this is really beautiful question in gate 2026. Let me tell you, in gate 2026, in set 1 there are two questions from vertex cover matching like that. In gate, in this session, did you notice in this session we have solved two questions of gate 2026 of set 1. In the same set there are two questions. One question is based on vertex cover, another question is based on matching. Okay, so these topics, matching, vertex cover, independent set, these topics, remember, clique, age cover, all these topics, remember, we have studied in a complete analysis way. All the gate PYQs, TIFR PYQs we have solved. Every question we have solved with complete analysis, with variations, okay, multiple methods to solve. I hope you are very comfortable now. Vertex cover, age cover, independent set, matching, and clique. These five concepts, their relationship, everything we have seen with proof, with complete analysis. I hope you understood everything. Now let me ask you some more important questions. All the gate previous year questions, TIFR previous year questions we have solved. All those are covered. But some more important questions I just want to ask you, and you can answer these questions because the concepts we have already studied. So I have full confidence on you. You can answer these questions. So let's see important question. In a graph G, any graph, this graph G can be any graph. Let P be the number of independent set in G and Q be the number of vertex covers in G. Then what is the relationship between P and Q? Can you tell me, in any graph G, if P is number of independent sets and Q is number of vertex covers, then what is the relationship between P and Q? This is your question number 1. Let me ask you another question. In any graph G, if P is the number of independent sets in G and Q is the number of cliques in G complement, then what is the relationship between P and Q? Let me ask you a third question. In any graph G, if P is the number of vertex covers in G and Q is the number of cliques in G complement, then what is the relationship between P and Q? These three questions, the concepts we have studied. Now you can easily answer these questions. Let's answer the first question. You can see in any graph G, P is number of independent sets, means in this graph, how many independent sets are there? The number of independent sets, that is P, and number of vertex covers, that is Q. What is the relationship between P and Q? Let's answer this question. So for this question, we need to know the relationship between independent set and vertex cover, and that we have already seen in our lectures with proof. So what is the relationship between independent set and vertex cover? You can see relationship between vertex cover and independent set. If S is independent set in G, then the remaining vertices V minus S will be vertex cover in G. And if S is vertex cover in G, then the remaining vertices V minus S will be independent set in G. So I can say S is vertex cover in G if and only if the remaining vertices V minus S is independent set in G. So remember, these two concepts are complementary in G itself. In a graph G, if a subset of vertices is independent set, then the remaining vertices will be vertex cover. And if a subset of vertices is vertex cover, then the remaining vertices will be independent set. So this relationship we know. We also know some more points, that if S is minimum vertex cover, then the remaining vertices will be maximum independent set. If S is largest independent set, then the remaining vertices will be smallest vertex cover. Also, we know that if S is minimal vertex cover, then the remaining vertices will be maximal independent set. And if S is maximal independent set, then the remaining vertices will be minimal vertex cover. So this is just a recap of relationship between vertex cover and independent set. Now let's solve this question. In any graph G, if P is number of independent set and Q is number of vertex cover, then what is the relationship between P and Q? The answer is P will be equal to Q. Correct? Means the number of independent set and the number of vertex covers will be same in a graph G. What is the reason? The reason is very simple, because you know that if S is a vertex cover, if S is a vertex cover in G, then you already know that this S, the remaining vertices V minus S will be independent set in G. Correct? Okay. And similarly, if S is independent set in G, then it will imply that the remaining vertices is vertex cover in G. Okay, very simple. This we already know. So it's like two ways. If V minus S is independent set, then the remaining vertices will be vertex cover. If V minus S is vertex cover, then the remaining vertices will be independent set. It's two ways. What it means? It means that in G, in graph G, if these are the vertex covers, notice if these are the vertex covers, let's assume these are the vertex covers. These are vertex covers, like let's assume this is vertex cover 1, this is vertex cover 2, this is vertex cover 3, and so on. This is vertex cover K. Then you know that you already know that if this vertex cover 1, if this is a vertex cover, then the remaining vertices will be independent set. So you can see for every vertex cover, there is a unique independent set associated with it. What is that? That is V minus VC1. Do you agree? You have graph G, V, comma E. So you can see that for every vertex cover, there is a unique independent set associated with it. This is independent sets. Similarly, for this vertex cover VC2, there is a unique independent set associated with it. Similarly, for this vertex cover VC3, there is a unique independent set associated with it. Okay, and so on. You can see V minus VCK. Remember, this is two ways. This is two ways. If you have any independent set, then also there is a unique vertex cover associated with it. So it's like two ways. It is two ways. So it is a bijection. It is a bijection. If you take any independent set, then there is a unique vertex cover associated with it. For any vertex cover, there is a unique independent set associated with it. Okay. So overall, I can say that number of vertex covers is same as number of independent sets. Very simple. Agree? So that's it. So remember what we can say, that in any graph G, in any graph G, the number of vertex covers, the number of vertex covers, that will be equal to the number of independent sets. That will be equal to the number of independent sets. Okay. I hope you understood. Also remember, if S is minimum vertex cover, then the remaining vertices will be maximum independent set. Also, if S is largest independent set, then the remaining vertices will be smallest vertex cover. So I can also say that the number of minimum vertex covers, the number of minimum vertex covers, that will be same as, that will be same as the number of maximum independent sets. Maximum independent sets. Okay. And similarly, I can say that the number of minimal vertex covers, that will be equal to the number of maximal independent sets. Because remember, for every vertex cover, there is a unique independent set. For every independent set, there is a unique vertex cover. Similarly, in any graph G, for any largest independent set, there is a unique smallest vertex cover. And for every minimum vertex cover, there is a unique maximum independent set. Similarly, in any graph G, for every minimal vertex cover, there is a unique maximal independent set. And for every maximal independent set, there is a unique minimal vertex cover. So I hope you understood this relationship. Clear? Now, notice just a small thing, that in any graph G, remember, if I ask you the number of minimum vertex covers, means how many minimum vertex covers are there, then that number will be equal to the number of maximum independent sets that we already know. We have just now we have seen. Okay, but understand the difference, that if I ask you size of minimum vertex cover, size of minimum vertex cover, size of minimum vertex cover, what is that? That is your beta. That is equal to what? That is equal to the number of vertices minus size of maximum independent set. Okay, that is your alpha. So I hope you understood this point. Understand the difference here, that in any graph G, how many minimum vertex cover we have, that is same as how many maximum independent set we have. But remember, the size of minimum vertex cover beta is equal to number of vertices in the graph minus the size of maximum independent set. Okay, I hope you understood all these points. Now tell me the answer for this question. In a graph G, P is number of independent set in G and Q is number of cliques in G complement. Then what is the relationship between P and Q? So to answer this question, you must know the relationship between independent set and clique. This relationship we already know. In our lectures, we have seen with proof. So relationship between clique and independent set. If S is a clique in G, then in G complement S will be independent set. And if S is independent set in G, then in G complement S will be clique. Basically, when you complement the graph, then clique will become independent set and independent set will become clique. Okay, so I can say that S is a clique of G if and only if S is independent set of G complement. So I can say these two concepts are complementary in G comma G complement. Okay. So you can notice one thing. In graph G, every independent set has a corresponding clique in the G complement. And in graph G, every clique has a corresponding independent set in the G complement. So again, there is a bijection. Yes or no? You can see in graph G, every independent set will have a corresponding unique clique in the G complement. Similarly, any clique in G complement will have a corresponding unique independent set in G. So again, there is a bijection here. So I can say how many independent set we have in G, that is same as number of cliques in G complement. Or I can say that how many cliques we have in G, that is same as number of independent sets in G complement. Okay, is this clear? These are some more points that we have already seen in our previous lectures, that if you complement the graph, then maximum clique will become maximum independent set. And when we complement the graph, then maximum independent set will become maximum clique. Similarly, when we complement the graph, then maximal clique will become maximal independent set, and maximal independent set will become maximal clique. Okay, all these points we have already seen in our previous lectures. So what will be the answer for this question? P is number of independent set in G, Q is number of cliques in G complement. What is relationship between P and Q? That also will be equal. Means P equal to Q. The reason is very simple, because in the graph G, this is your graph G. In this graph G, if you have some independent set 1, then there is a corresponding unique clique in G complement. In G complement, there is a corresponding unique clique in G complement. Okay. So you can see whatever independent set you take, there is a corresponding unique clique in G complement. Similarly, whatever clique you take in G complement, there is a corresponding unique independent set in G. Okay. So again, there is a bijection here. Very simple. I hope you understood. So you can see, for example, if this independent set is, let's assume y1, then this will become clique in G complement. And if you have a clique, let's assume clique is z1 in G, then remember that will become independent set here. That will become independent set here. So I hope you understood the point, that y2, y3, y2, y3, like that. So you can see every independent set of G has a corresponding unique clique in G complement, and every clique of G complement has a corresponding unique independent set in G. Okay, so it's again a bijection here. So I can say number of independent sets in G, that will be equal to number of cliques in G complement. Okay, that's it. So very easy. So finally I can say this is the relationship, that number of independent sets in G, that is equal to number of cliques in G complement. Okay, very simple. Similarly, number of cliques in G, that will be equal to number of independent sets in G complement. Okay, easy relationships. Let's see this question. Let P be the number of vertex covers in G. Let Q be the number of cliques in G complement. What is the relationship between P and Q? Again, this will be equal. But why? What is the reason? Let me tell you. See, we have already seen that number of vertex covers in G, that is equal to number of independent sets in G. This we have seen. This was our equation 1. And we have seen that the number of independent sets in G, that is equal to the number of cliques in G complement. This is our equation 2. From these two equations, what can you say? From these two equations, so I can say that number of vertex covers in G, that will be equal to number of independent sets in G, and this number of independent sets in G, that is equal to number of cliques in G complement. So I can say number of vertex cover in G, that is equal to number of cliques in G complement. Okay, very easy. Yes or no? So number of vertex covers in G, that is same as number of cliques in G complement. Very easy. Okay, so everything we have seen, and these are the two results. You can see result 1, result 2. The number of vertex covers in G, that is equal to number of independent sets in G, and the number of independent set in G, that is equal to the number of cliques in G complement. Because you already know that S is independent set in G, then S will become clique in G complement, and if S is clique in G complement, then it will become independent set in G. When you complement the graph, then independent set will become clique and clique will become independent set. So from these two, I can also say that number of vertex covers in G, that is equal to number of cliques in G complement. Okay, so basically number of vertex cover in G, that is equal to number of independent set in G, that is equal to number of clique in G complement. This is the overall conclusion, this is the overall summary. Okay, and these results, these are not fancy results, these are very easy based on the concepts that we have seen. Yes or no? So everything is actually very easy. We understood the concepts with proof, then we have solved all the gate PYQs, TIFR PYQs, then some standard questions, some variations with complete analysis. So that's it. This is your chapter. All the gate PYQ, TIFR PYQ we have covered. So remember these concepts: vertex cover, matching, edge cover, independent set, clique. These concepts we have studied with proof, and also all their gate PYQs, all their TFR PYQs we have solved with complete analysis. Okay, in this playlist you can find everything. You can search on YouTube discrete mathematics go classes, and this playlist contains all the gate PYQs, compact course, practice questions, revision, everything. Okay, so thank you everyone. Please share your feedback in the comments. Let me know, did you understand everything? Did you enjoy this lecture? If you have any doubt, you can put in the comments. So please put a comment and let me know your feedback. Okay, thank you everyone.